Fortunately, although I presented the theory last week, which is in the slides which are on Blackboard, and obviously in the notes, what you need to know for this stuff is how to use it, okay? And you can get that from the examples in the notes and the examples that I'm going to do today, okay? So that's what we're going to do today. And hopefully, through working through the examples, you'll get an idea of what this is all about. But I thought I'd just give a very brief introduction to what it was and go through the procedure that we need to go through, like I said, and then we'll go through a couple of examples today, one of which is in your notes, and the other one of which is not in your notes. Right. So the subject of the lecture was modal analysis, okay, which is a way to deal with problems where you've got lots of modes of lots of degrees of freedom, okay. And the issue that we have with the normal process for solving problems with degrees of freedom is you end up with some differential equations that are all coupled together, okay. They're linked to each other, and you have to solve them simultaneously. Whereas modal analysis allows us to separate those equations into separate differential equations where you can solve each of them individually, which is a lot easier, okay. Now back in chapter 3 we went through solving differential equations, okay, as one of the ways to deal with a single degree of freedom systems. And what we can do is we can use the solutions that we used in chapter 3, that we found in chapter 3, to solve these problems, because often the equations will have the same form as the equation that we solved in chapter 3. So that's the whole point of modal analysis. And like I said, what we did last week is we went through the theory and then we went through a couple of examples on the big screen, okay, but the ones that are in your notes. Today we're going to go through some more examples, but this time I'm going to write them, and so one of them will be a solution to the questions you've got in your book, and the other one, like I said, is not in your book, and that's because it's from last year's exam paper. For these examples, there's a procedure that you can follow. Okay, there's 8 steps, and I'm just going to go through them very briefly. The first three steps you should know how to do already, because this is the basics of multi-degree of freedom systems. You first off find the equation of motion in matrix form, okay? That you can either use Newton's second law, or if you're adept, you can use the quick method that we discussed in chapter 5, where you fill out the mass matrix, the stiffness matrix, and you set up your equation of motion in matrix form. You then make a substitution, either using the cosine or the exponential. The details are in the notes, and using that substitution, you can find what's known as the mechanical impedance matrix. Okay, and from that matrix, you find the determinant. You can then get the natural frequencies, and by applying those natural frequencies back to the mechanical impedance matrix, you can then get the mode shapes. Great. So we've got the equation of motion, the natural frequencies, and the mode shapes. Step 4 is where we start diving into the theory of this chapter. You have to find the modal mass and the stiffness matrices, okay? I'll show you the equation of this in a minute. Modal mass and stiffness matrices, you then rescale the unit modal mass, and you find what's known as the modal matrix, which is this key that we talked about, where you can unlock, you convert your equation of motion into a set of uncoupled equations, they're modal equations, that you can then solve individually. Obviously, if there's a force being applied, you've got to deal with that. You need to convert that into an appropriate form. You then solve those equations. Like I said, you can often use the solutions in chapter 3 to solve. And then you can have to convert those equations back into displacements to get your complete solution. So that's the process that we're going to go through. Like I said, steps 1 to 3 you should know how to do already, and steps 4 to 8 is what's covered in this chapter. So let's go through an example. We did the examples that were in the notes last week, and this time we're going to actually go through one of the solutions to the problems that you have. Problems are on page 107. And we're going to go through the solution to question 1. Here goes. Is that clear? question 1. We have a system that looks a little bit like that. We've got M here, 2M, and then the spring stiffnesses are K, 3K and K. Okay, and we've got, here is X1, X2, and we've also got a force on F1. Okay, we've been given some values. K is 100 kilograms. Sorry, 100 newtons per meter. Let's erase that. M is 1 kilogram. And F1 is 5t newtons, and that's from t is greater than or equal to 0. Okay, and we've got to find the response of the system using the results given in the notes, okay? Because this is basically, it's the same problem as worked example 2, which starts on page 102, okay? But what I'm going to do is I'm going to go through all the steps, because this will help reinforce the process. So, step 1 is equation of motion, E dot O dot M. Okay, so we can say our mass matrix using the quick method, where we've got two masses, M and 2M, and so we have M here, 2M here, 0 and 0. There's our mass matrix. Newton's second law says it's multiplied by acceleration, so we have x1 double dot and x2 double dot, plus, and then we have our stiffness matrix. There's no damping. So the first box is the sum of the masses connecting each mass to ground or to another mass, and so here we have 4K. And then for the second mass we've got 4K as well. And then for the masses, the spring between the two masses, we've got minus 3K and minus 3K. And that's multiplied by displacement, x1 and x2. And then we have our forces. We've got 0 for force 2 and 5t for force 1. When we're converting it to the mechanical impedance matrix, we actually set this force to 0 and 0, because that's the free response that we're looking for. And we apply the substitution. So this is step 2. We're going to set x equal to big X cosine omega t plus phi. So that means that x double dot is going to be minus omega squared x cosine omega t plus phi. We stick that into this equation and we get the mechanical impedance matrix. 4k minus m omega squared minus 3k minus 3k and 4k minus m omega squared. So we have to find the determinant of the mechanical impedance matrix. The determinant of this thing, which is those two multiplied together minus those two multiplied together. So we've got this equation, and then we can therefore simplify that down. I'm going to skip a few steps, but if you go through the maths, this is what you should get. 2 m squared omega to the power 4 minus 12 m k omega squared plus 7k squared. And we can see that that is a quadratic equation in terms of omega squared. So we can find out what omega squared is using the quadratic formula. And so we have omega 1 squared is going to be 0.655 k upon m. And omega 2 squared comes out to be 5.345. Yes? It should indeed. Yes. Well spotted. Don't apologise. It shows me that you're awake, which is a good thing. So, we find the equation of motion using the quick method. We make the substitution to get the mechanical impedance matrix. You find the determinant of the mechanical impedance matrix to get your omegas, omega 1 and omega 2. You then stick those values for omega back into this equation, into your mechanical impedance matrix, which I've done. Okay, and you solve for 1 over r1, setting x1 to be 1. R1 will give you the relative displacement of x1, sorry, of x2 relative to x1. Okay, so that's what you do. And if I go through this process, I get 3.345 minus 3r1, and that comes out to be 0. So that means that r1 must be equal to 1.115. For mode 2, it's the same process. But then instead of 0.665, we've got 5.345 k minus 3k minus 3k, and then 4 minus 2 times 5. So we find R1 to be 1.115. So there's the first mode shape, 1 and 1.115. And then the second mode shape, we find R2 to be minus 0.448. So we have 1 and minus 0.448 as the second mode shape. Okay, so here's our two mode shapes. So we found our two mode shapes. We then start step 4, okay, which is to find the modal masses. And the equation for the modal masses is so I'm going to call this mode shape I, it doesn't matter, times by your mass matrix, and that's transposed. Okay, and that equals mi. This is the equation that you need to use for the modal masses. And so we take the first one, for mode 1. We have 1.115, so there's the mode shape transposed. We have our mass matrix, which is m, 0, 0, 2m, and we have 1 and 1.115 here, equals m1. Now what we can do is we can, since we know what mass is, we know that the mass is 1 kilogram, so m must be 1. 2m is obviously 2. And so we can actually go through and solve this. If you follow the notes, we found that m1 was 3.486 m. So this is 3.486 1.486. And we found this to be 1.4014. So that's step 4, finding the modal mass. This is the equation we have to use to find the modal mass, okay, which is the transpose of your mode shape times by the mass matrix times by the mode shape again, okay? So you end up getting big M1. You do this, the matrix multiplied by the mode shape first, then multiplied by the transpose of the vector, and you end up getting M1 comes out to be 3.486 when M is 1, which is what it is in the question. And we do the same thing for the second mode shape, and we get M equaling 1.014. You don't need that M there, because M is 1. Step 5. We have to rescale those mode shapes so that M1 becomes 1 each. Okay, so this means we've got to define U I equals X I divided by the square root of M I. This rescales those things so we can find a modal vector that results in unity for the mass part of the equation of motion, or the acceleration part of the equation of motion. So we end up with, for mode 1, we have 1.115 divided by the square root of 3.486. And that comes out to be, so this is U1, 0.536, 0.598, and for mode 2, so there's our two U values, and then you can obviously combine them to find the modal matrix. So, that was step 5. Step 6 is we've got to deal with the applied force. Okay? Where F of t equals the modal matrix transposed times by our applied force. Okay? The other advantage of modal analysis is that we can apply forces to our multiple degree of freedom problem and solve it. Okay? If you remember from chapter 5, all the equations of motion that we came up with were when you had free oscillation. There was no forces being applied. Here we've got applied forces and we can solve the problem. And so we've got, I'll call this F1t and F2t. We've got our transposed modal matrix, that's 0.536 here, 0.598 here, 0.845 minus 0.379. So that's our transposed modal matrix, and then we have F1, which is 5t, and 0. And so if you do the sums, we've got 0.536 times by 5t, okay, which comes out to be, what is it? 2.68. And then for the second one, we've got 0.845 times by 5. This is t, obviously. We've got 4.225. There's our applied forces. So we end up with an equation that looks like this. And that's the equation for a linearly increasing force, and it matches up to the equation in chapter 3 that looked a bit like this. Okay? And the solution to that equation, this one here, okay, was x equaling minus f naught upon omega. Okay, that was the solution for this second equation. So therefore, qi must be equal to minus ci divided by omega I cubed sine of omega I t plus ci t divided by omega I squared. And that's because we can see that m1 is equal to 1. Because m equals to 1, k equals omega I squared, and f naught equals ci. Okay, you can match up these two equations. Where's the thing gone? You can match up those two equations, and you can see that m is 1, and k must be omega I squared, and f naught must equal ci. And so because you can match up those terms, this equation must mean that q is this equation. Okay? And that's linearly increasing force. This equation is on your formula sheet. You'll see when you go through the exercises of this chapter that one of the exercises that I've given you is where you've got an exponentially decaying force or exponentially increasing force. I can't remember. It's on the notes. Yes, exponentially decaying force. And so you have to apply the same equation that you found in chapter 3 for an exponentially decaying force as well. And again, that solution is given in the solution when with initial rest conditions is given in the notes in the equation sheet in the exam. Okay, so there we go. There's omega 1 cubed and omega 2 cubed, so we can plug them into this equation now. We end up with Q1. We've got 2.68 divided by 530.7 sine 8.09 t so that's where omega 1 comes from, because if you square root that, you get that. And then we have plus, there's a minus sign here. And then we've got omega squared, so 65.55. There's the equation for Q1. And Q2 minus 4.225 divided by 12,367 sine of 23.12 times by t plus 4.225 divided by 535, so it's 134.5. And you could you can multiply this out if you really want to, which is fine to do. So that's Q1 and Q2. And so what you do is the modal equation is always going to look like this up here, okay? For a linearly increasing force, you'll have some constant times by time. And we've solved that equation, but in this form in chapter 3. And the solution in chapter 3 we found to be this, for initial rest conditions. Obviously, if you haven't got initial rest conditions, you have to work out what A1 and A2 are from the general equation. And so if you match up the coefficients here to this equation, you get this equation for Qi, okay? And it's just a matter of plugging in the numbers, because m equals 1, k must equal omega I squared, and f0 must equal ci. We've got c1 and c2 here. We know m is 1, okay? This m doesn't actually feature in this equation. And omega I squared is k. So omega I squared, well, we've got those values. We found that. This is from earlier on in the question. Let's make this look a bit more like a bracket, shall we? Okay. In fact, reorganising stuff on this screen is a nightmare. So I'm just going to rewrite it. Okay. Those two equations are from earlier on in the question. Okay. And because we know that k is 100, we've got 65.55 and 534.5. To find the cube, obviously you square root this and then cube those values and you get those two numbers. Okay. And obviously to find omega 1 and omega 2, which you need to stick in the sine bit, sine omega 1t and sine omega 2t, you have to obviously square root this. You get 8.09 for this one and 23.12 for this one. And so that's where those two come from. So we've got omega 1 squared, omega 1 cubed, and omega 1. And then you plug in the numbers into this equation. Well, C1 was 2.68, so there's there. 530.7, which is this value here. Sine of 8.09t, 8.09t, plus 2.68t, because it's C1t, divided by omega 1 squared. So that's 65.55. And then obviously here I've just divided these two together to get this number, sine of 8.09t plus 0.41t, which is those two numbers divided by each other. And then you could do exactly the same process for Q2, except for you this time you've got some different numbers. And so you plug in those numbers and this number, and you get an equation for Q2. So like I said, what we've done is we've broken that question down into two uncoupled equations. One for Q1 and one for Q2. And because we know the solution to that, because we found it, you can go through and apply the solution and you get those two equations. Okay, so that's step 7. Step 8 is merely applying the key again. So we have x1 and x2. There's a solution. Okay, where if you left the answer of the question in that form, that's fine, okay? And obviously you've got Q1 and Q2 down here, as that's part of the solution. And you can see what's happening. We have got a linearly increasing force being applied to one of the masses in that 2 degree of freedom system. And obviously what's going to happen is that you're going to have mass 1 increasing linearly by a certain amount, okay? 0.536 times 0.0412, and mass 2 is also going to be increasing. Plus this value. Okay, so that's again linearly increasing, and then you've got the same thing for x2, but they're both going to have small ripples in. Okay, which is the fact that there's no damping, so they're going to both be oscillations. And those ripples are at different frequencies and by differing amounts. So that's question 1 from your notes.